Now that we know about moles and molar mass, and now that we know how to use the molar mass equation, we can start doing some very useful calculations involving chemical formulas. One of these calculations involves determining empirical formulas and subsequently chemical formulas. Now, if we had a sample of matter containing a compound whose identity we didn't know, we could send that sample off to an analytical laboratory for elemental analysis. Elemental analysis is a process whereby a sample of matter is analysed for its elemental composition, and often the results come back to us in terms of the mass percentage of each element involved in the compound. So for example, a compound containing calcium, carbon and oxygen could come back with the results that the compound contained 31.3% calcium, 18.8% carbon and 50% oxygen. Now I know of at least two compounds that could contain calcium, carbon and oxygen. One of them is calcium carbonate, where the ratio of calcium carbon to oxygen atoms is 1 to 1 to 3. Another compound that it could be is calcium oxalate, and here the ratio of calcium to carbon to oxygen atoms is 1 to 2 to 4. So the data that we get back from elemental analysis can't tell us directly what this ratio is, but we can now use our knowledge of moles and molar mass to actually help to determine the empirical formula and therefore the chemical formula. So the percent composition data can be used to determine empirical formulas and then subsequently empirical formulas of compounds. And we should just remind ourselves what an empirical formula is. It's a chemical formula where the subscripts are in the lowest whole number ratio of the elements involved in that particular compound. We should also remind ourselves that for ionic compounds, the chemical formula is already written in the lowest whole number ratio of all the elements involved, and so the empirical formula and the chemical formula are the same for ionic compounds. Now that's not the case for molecular compounds, where the chemical formula is a whole number multiple of the subscripts involved in the empirical formula. So a typical problem that we might get here is shown here. Elemental analysis of a compound shows it contains those three percentages that we just saw a moment ago: 31.3% calcium, 18.8% carbon and 50% oxygen. And we're being asked to determine the empirical formula and the chemical formula. So we can write down an expression for the empirical formula straight away: CaXCyOZ, where the subscripts X, Y and Z are the subscripts, the whole number subscripts in the empirical formula. And if we can determine what the values of X, Y and Z are, we effectively have the mole ratio of X, Y and Z, and therefore we have the empirical formula. Now when we've written our empirical formula down as CaXCyOZ, what we've done is written the most electropositive element first, that's calcium. We've written the most electronegative element last, that's oxygen. The most electropositive element is left and down in the periodic table, and the most electronegative element is right and up in the periodic table. So calcium appears over on the left hand side in group 2, so it's the most electropositive of these three elements. Oxygen is over in group 16, which is on the right hand side of the periodic table, and it's up in period 2 as well. So oxygen is right in the periodic table and up high in the periodic table. So it's the most electronegative of these three elements. We're writing it last. And carbon lies in group 14, so it sits in the middle. So we're writing them from left to right: calcium, carbon, oxygen. When answering these types of questions around empirical formulas and chemical formulas, and if we're given mass percentage data, a neat little trick here is to assume that we have 100 grams of the sample, because if we have 100 grams of the sample, then the 31.3% of calcium actually says that we have 31.3 grams of calcium, and that the 18.8% of carbon in that 100 gram sample means we actually have 18.8 grams of carbon, and the 50% of oxygen in that 100 gram sample means that 100 gram sample, 50 grams of it is oxygen. Now if we've got mass quantities of each element, we can actually now work out the moles of each element, because we can use our molar mass equation. We've got the mass, and all we need to be able to do is determine the molar mass, and we can get that straight from the periodic table. So we're now in a position, if we assume we have 100 gram of sample, to work out the moles of calcium, carbon and oxygen by using the equation moles equals mass on molar mass. And by getting those moles, what we're actually getting will be the mole ratio of each of those elements, and then that will give us the empirical formula. So we'll set that equation aside there. Moles equals mass on molar mass. And we'll start with our calcium calculation. Moles equals mass on molar mass. We've got the mass of 31.3 grams, and we're dividing it by the molar mass of calcium. Now remember, we're just going to get that number directly from the periodic table. The atomic mass for calcium, 40.078, and we're going to report the molar mass therefore as 40.08 grams per mole to 4 significant figures. When we put those numbers into our calculator, we get 0.7809 moles of calcium in our 100 gram sample. We can do the same for the moles of carbon. We've got a mass of 18.8 grams in our 100 gram sample, and we're dividing it by the molar mass of carbon. And remember, we just get the molar mass value directly from the periodic table and express its units as grams per mole. So 18.8 divided by 12.01 gives us our 1.565 moles of carbon in our 100 gram sample. We can do the same for the moles of oxygen. We've got 50 grams of oxygen in the 100 gram sample, and we're dividing it by the molar mass of oxygen, which we get directly from the periodic table, 16.00 grams per mole to 4 significant figures, and we get a value of 3.125 moles of oxygen. So in our 100 gram sample, we've now actually worked out how many moles of calcium we have, how many moles of carbon we have, and how many moles of oxygen we have. And each of these moles are effectively the moles in the empirical formula. So we can say that the 0.7809 moles of calcium is related to that X subscript. The 1.565 moles of carbon is related to that Y subscript, and the 3.125 moles of oxygen is related to that Z subscript. In fact, we could even write out a chemical formula with those numbers represented. But this chemical formula we know doesn't make any sense, because whether it's an empirical formula or a chemical formula, the subscripts need to be whole numbers. And so we need a way of getting these numbers as whole numbers while still representing these ratios of the moles of calcium, moles of carbon, and moles of oxygen. The easiest way to do this is to identify the amount of moles calculated that has the least number of moles. So the 0.7809 moles is the smallest number of moles calculated. It's the moles of calcium are smaller than the moles of carbon and smaller than the moles of oxygen. And what we actually do is we divide each of these numbers by that smallest number. So the 0.0809, divide it by itself. And then we divide the 1.565 by that 0.7809. And we also divide the 3.125 moles of oxygen by the moles of calcium, 0.7809. And of course the numbers we get out now, we get 1 for calcium, 0.0809 divided by itself is 1. 1.565 divided by 0.0809 is 2. And 3.125 divided by 0.0809 is 4. And in effect, they become the subscripts in the empirical formula. So our empirical formula we've now calculated to be Ca1, C2, C2O4, or in other words, CaC2O4, remembering we don't explicitly write the ones in chemistry. This compound here is the chemical formula for the ionic compound calcium oxalate, and the ions involved are the Ca2 plus ion and the C2O4 2 minus ion, the oxalate ion. As I said, this is an ionic compound, and we've already noted previously that the empirical formula and the chemical formula for an ionic compound are identical. So CaC2O4 is not only the empirical formula, it's also the chemical formula in this case. So by working out the percentage mass of each element in a compound and using our molar mass equations and assuming a sample of 100 grams, we've been able to work out both the empirical formula and the chemical formula for this ionic compound. In a subsequent video, we'll deal with a molecular compound where we'll see that the empirical formula and the chemical formula are not the same.